Okay, for our final segment, we want to talk about graphing. And so we're going to be interested in making distance versus time graphs. And then we're also going to be interested in making speed versus time graphs. And we want to be able to look at a graph and interpret what is it that it's trying to tell us. So the equation for a straight line on any kind of a graph is going to be y equals mx plus b. It's kind of unfortunate that they use the letter m because in physics we like to use m for mass. But this time this m is going to stand for slope. And so the slope of a line is going to be its rise divided by its run. So that if on this thing we make it into a little triangle there, this thing over here is going to be called the rise, so the distance from here to here, and then the distance from here to here, that's going to be called the run. So if we take the rise and then we divide it by the run, then that's going to be the slope. And then also notice that if we make it taller, so let's say that we make it like this, what do you think that does to the slope? It's going to make it greater. So this has a greater slope than this one. And then what would this mean if it's horizontal? That means it doesn't have any slope. So the slope would be equal to 0. And then what do you suppose it means if it's doing that? That then would be a negative slope. So you have all sorts of different kinds of slopes. And then this thing over here, so you got the slope times x. Now this is y, is always going to be up and down. And then x is always going to be sideways. The b is going to be called the slope intercept. And so what that represents is this distance right here. So wherever the line intersects the y-axis, that then is going to be the slope intercept. Okay? So it's important that you understand the formula for a straight line and then also the formula for the slope of a line. Okay, now that we know that, let's analyze in particular different kinds of lines and curves that result from the motion of objects. So we're going to start off with a distance versus time graph. Okay, so now we've got this one here. So R is going to be plotted going up and down, and then time is going to be plotted going sideways. All right, now let's do something stupid. All right, let's say that you've got a car and it's just sitting there. It's not moving at all. What would its graph look like? Okay, let's say that it's at rest at the point 0. So 0 on our ruler. So that would mean it plots right here. Okay, now what's going to happen to it? At the end of 1 second, where's it at? Well, it's still there. It hasn't moved any. So at the end of 1 second, we would plot it like this. So in the R direction, it's still on 0. Time has changed, but the distance is not. And then at the end of 2 seconds, and at the end of 3 seconds, so if we connect all of these lines together, we get this. So it's just going to be sitting there. So that one represents how it would graph out if it was just sitting there. Now, what about, though, if it's traveling at a constant speed? So what would that mean if it's traveling at a constant speed? So let's say that it's traveling at 1 meter per second. So let's say that at the end of 1 second, it would be at 1 meter. And then at the end of 2 seconds, it would be at 2 meters. And then at the end of 3 seconds, it would be at 3 meters. So I'm trying to draw this so that we've got 1 meter, 2 meters, 3 meters. 1 second, 2 seconds, 3 seconds. And so if we connect it all together, then we get this. So that if something is moving at a constant speed, it's going to have a straight line on a distance versus time graph. And now let's calculate what the slope would be. So we would do a rise over run. But what is the rise? The up and down part? That's R. So R is our up and down part. So therefore the slope is going to be equal to R. And then the run part is the sideways part. That's the T. So did we learn anything today about what is distance over time? What was that called? Speed. So therefore the slope of a distance versus time graph is going to be the speed of the object. And if it is going at a constant speed, it's a straight line. But what about if it was accelerating? So what if its speed was changing? Well, then what would be different about the graph? Well, we would still have 1 second, 2 seconds, and 3 seconds. But what about the distance? So it's going to be going at, it will travel a certain distance to begin with at the end of, let's say, 1 second. So at the end of 1 second, it has traveled a certain distance. So let's go ahead and say it's right there. At the end of 2 seconds, it will have gone further because it has a faster speed. Acceleration changes your speed. Speed changes your distance. So if it's going faster, then that would mean that it's now going to be maybe up here. And then at the end of 3 seconds, it's going to be going even faster. So what you end up with is a curve. So on a distance versus time graph, if something is accelerating, then it's going to have a curve to it. If it's going at a constant speed, it's going to be a straight line. Now we could even calculate the slope of this curve if we wanted to. We'd need to pick out 2 points on the curve and then turn it into a triangle and then calculate rise over run. And so we could do that if we wanted to. So those were the 2 curves in that first picture over there, illustrating what does motion at a constant speed look like, and then what is motion when you are accelerating? What does it look like? Now let's look at this one over here. So this one is the speed of an object versus time. So again, let's do something really stupid. Let's say that it's not moving at all. So it has a velocity of 0. What's it going to look like? So that means when you click your stopwatch, it has 0 speed. Okay, at the end of 1 second, it's still sitting there, so it has a speed of 0. And then at the end of 2 seconds, so you see that you're getting a horizontal line down here at the bottom. That's not very exciting. So now let's say it has a constant speed. Okay, let's say 2 meters per second. So we would go up here, so this would be 1 meter per second, and then let's just say that that's 2 meters per second right there. So when you click your stopwatch, it would be going at 2 meters per second. At the end of 1 second, how fast is it going? 2 meters per second, because I said it's going at a constant speed. And then at the end of 2 seconds, it's over here. And so now this is what it looks like. You'd have a horizontal line, and it depends on the speed. So the faster it's going, the higher up it would be on that chart. So now let's talk about acceleration. So what is it going to look like when it is accelerating? So that would mean that when we click our stopwatch, let's say that it's not moving. So we're going to start it right here. Okay, at the end of 1 second, it's going to be going at a certain speed. So let's say 1 meter per second. So that puts it right about here. Now at the end of 2 seconds, if it is accelerating, what's happening to its speed? It's going faster. So at the end of 2 seconds, maybe it's up to here. So it was going at 0 meters per second, 1 meter per second, 2 meters per second, and then we could go even further and say maybe it's up here. So notice that you have a line that makes a slope if it is accelerating. So what do you suppose is the significance of the slope? So we could calculate that slope of that line there. What does it mean? So the up and down part is velocity, and then the sideways part is time. So the slope this time would be the change in velocity over time. And did we have a special name for that? Yes, we did. We said it was the acceleration. So the slope of a velocity versus time graph is the acceleration of the object. The slope of a distance versus time graph is going to be the speed of the object. Now you notice that it's not quite symmetrical. So you notice this one's got horizontal and it's got a diagonal, horizontal and then a diagonal. So you might be wondering, well, what about this one? What about one that curves? Well, that would be meaning that the acceleration is changing. And do you remember that we said we wanted to keep the acceleration constant? So you would never see that line unless it was kind of unusual circumstances. Okay? So you only have curved lines on this particular graph. So on the exam, if you're one of my students, I could give you a graph, I could ask you to plot the graph, and then I could ask you to interpret the graph. What is the object doing? Okay, so there you go. All right, let's take a break, and when we come back, we will do our lesson quiz.